Okay, assalamu alaikum everyone. Let's start. We were doing vectors, and today we want to continue and discuss the next concepts that we have in this. We're done with a number of things, a number of concepts already. For example, we've talked about position vector of a point, magnitude, addition, subtraction of vectors, multiplication of vectors, unit vector, multiplication of two vectors using dot product, and then using that dot product to find angles between vectors. And we have discussed perpendicular vectors and parallel vectors. Okay, so these are all different things that we've done until now. In the last session, we did a number of practice questions on the concepts that we had covered at that point. Now let's start with the next concept that we have in this topic, and that is vector equation of a line. Vector equation of a straight line. Remember, in coordinate geometry, we did equations of lines already. So we learned how to find equations of straight lines. We learned how to find equations of straight lines in coordinate geometry. The standard form that used to be for a straight line was this: y equals mx plus c. Right? This was the standard form for the equation of a straight line. We needed two things for this particular form, and they were m, which is the gradient of the line. What exactly did it use to tell us? It was a number that gave us the direction of line, essentially. All right, how steep the line is, and is that number positive or negative? That also used to tell us whether the line's direction is like this or this. So gradient kind of tells us the direction of line. Okay. And then the second thing that we used to have there was the y-intercept in this particular form. And in the other form that we had, y minus y1 equals m into x minus x1, it could basically be any point. Y-intercept as well, it's actually a point that we have, but it's a particular point, the point where the graph intersects the y-axis. But you can say that this is a point that we had there, right? So in order to write the equation of a straight line, we needed two things. One was the gradient, which gave us the direction of the line. And the other was a point that gave us 1 point on the line. Okay, the y-intercept that gave us 1 point on the line. Now, there's another way of writing equations of straight lines, and we can use that other method to write equations of lines in 3 dimensions as well. We could use that for 2 dimensions as well, but we primarily use it for more than 2 dimensions, because for 2 dimensions, this is simpler to use. But when we talk about 3 dimensions, we normally use vector equations in that case. Now, first of all, let's try to understand the form that we have there for the equation of a line. For 2 dimensions, this is what the form used to be: y equals mx plus c in coordinate geometry. Now, for 3 dimensions, we use vector equations. Now, let's first talk about the standard form and how to use that, and then we'll briefly discuss where that form comes from. Vector equation of a straight line. All right. So in vectors, we write the equation of a line like this: R equals A plus lambda D. This is the standard form of the equation of a straight line. Okay, R equals A plus lambda D. Now, what do these different things represent here? A, lambda, D. What exactly do we mean by each of these things? Now, this thing A here, this means this basically is a point on the line. All right, A is a point on the line. Let me write that here on the side. this A is actually the position vector of a particular point on the line. Okay, so you'll have the position vector of one point that lies on the line. You would write that here in place of A. Okay, so A here is a known point. In fact, it's the position vector of a known point on the line. That's what A here means. Okay, now what about D? D is the direction of the line. This is called direction vector of the line. Where do we get this from? This is actually any vector that is parallel to the line, right? How do you find the direction of something? Or how do you know two vectors are in the same direction? They are parallel. So if you have any vector that is parallel to this line, that is going to give you the direction of the line. So you can use any vector that is parallel to the line as the direction vector. So this is any vector that is parallel to the line. That's what D represents. So in order to write down an equation of a straight line in 3 dimensions, these are the two things that we need. Okay. A and D, I'll come to what these things mean, R and lambda. But let me write down an example equation first of all. So for instance, you could have an equation that looks like this, for instance. R equals -2, 4, 1 plus lambda into 1, 3, 7. This is one possible equation of a straight line. And with, in this case, -2, 4, 1, this is a particular point on the line. So you would be given this point, that this point lies on the line. The position vector of that point is -2, 4, 1. You would write that in place of A here. Okay. And D is the direction vector. So in this case, 1, 3, 7. This is the direction vector of this line. Okay. Now, what about R and lambda? Remember in this coordinate geometry form that we used to have earlier, if we had an equation like this, y equals 2x plus 3, we did not used to write down any value for x and y here, because what we mean by this equation is if we have a line like this that has equation y equals 2x plus 3, every point on this line is going to satisfy this equation. So basically, how do you get different points on this line? You could input different values of x. So you input x equal to, for instance, if you want the value of y at a particular value of x, let's say at x equals 0, that gives you y equal to 3. And you get one point on the line, which is 0, 3. All right. If you input x equals 1, for instance, you get y equal to 5. And that gives you another point on the line that is 1 and 5. So xy, what does this represent? Xy is a general point on the line. Xy is a general point on the line. In this case, if we input different values of x here, we get corresponding values for y, and these are the particular points that we get. And similarly, you could try inputting other values of x here as well. Okay, so x, y, they represent a general point on the line. Now, in this equation that we have here, R basically represents a general point on the line. So let me just write that here. This R is the position vector. Remember, whenever we talk about points in 3 dimensions, we talk about their position vectors. Okay, we don't say coordinates generally. We say what their position vectors are. So R is the position vector of a general point on the line. So basically R represents a general point on the line. What about lambda? Lambda is actually a parameter and it can be any real number. Lambda can be any real number. Now just hold on with me for a few minutes and you'll understand what we mean by this. Lambda basically can be any real number. So you can input any particular value of lambda here, and different values of lambda in this are going to give us different points on the line. Now, what does that mean? Remember, in this equation, we used to input different values of x to get corresponding values for y. Now, it's slightly different in a vector equation. If a vector equation looks like this, minus 2, 4, 1 plus lambda 1, 3, 7, we know that this is a point that lies on the line, minus 2, 4, 1. Okay. What about every other point on the line? So let's say this is what the line looks like. And we have this value, this point, and this point has a position vector minus 2, 4, 1. And we know this point already. This is the point that we used to write down the equation of the line, minus 2, 4, 1. Now, what about every other point on the line? So this whole line is what this equation supposedly represents. Okay. So every point on this line is going to be represented or is going to satisfy this equation. So this line equation represents every point on this line. So how do you find every other point on the line? Basically, different values of lambda give you different points on the line. So for instance, if you input lambda equal to 1, for instance, what do you get from that? If you input lambda equal to 1 here, that gives you r equal to minus 2. If you input lambda equal to 1, you get minus 2. So, okay, let me actually just write like this for now. Minus 2, 4, 1 plus 1 into 1, 3, 7. What does that result in? Let's figure this out. This is equal to minus 1, 7, and 8. This is another point on the line. Okay, so if we input lambda equal to 1, we get another point on the line. It might be somewhere here. Okay, so that's another point on the line. If you input another value of lambda, you get another point on the line. So let's say if I were to input lambda equal to minus 2, that is going to give me r equal to minus 2, 4, 1, minus 2 into 1, 3, 7. This gives us another value of lambda and another position vector, which is minus 2 into 1, which is minus 4. Then 4 minus 2 into 3, that's minus 2. 1 minus 2 into 7, that's minus 13. This is another point that we have on this line. Okay, so lambda equals 1 gave us 1 point. That was somewhere here. The second point might be somewhere here because it's the other value of lambda was positive. So that will be on, if that is on one side of the line, lambda equals minus 2 is going to give us a point on the other side of the line. So just like this, if we were to input different values of lambda here, we'd get different points on the line, and every point on this line would therefore be represented by this equation. Why? Because you could try inputting lambda equals 0.1, for instance. That would give you, let's say, this point here. Okay. If you input lambda equal to 2, lambda equal to 0.2, you'll get another point here. 0.3 might give you here, 0.4 might give you this. And similarly, you could also input 0.01, 0.001, and you can get every point on the line like this. So that is what we mean when we say this. Lambda can be any real number. Remember, any real number means it could be any value in decimals, 0.0001, 2.3457. So basically any value. And different values of lambda are going to give you different points on the line, therefore. Okay, so you could have the value of lambda between minus infinity to plus infinity. Any value that you give gives you another point on the line. Okay, now R is the general point on the line. So you can see R is equal to different position vectors depending on the value of lambda. So this whole thing is going to evaluate to something depending on the value of lambda. So that's why we are saying R is a general point that we have. We often write R in this form as well. You could say this is X, Y, Z. That's the general point that we have on the line. It's in this form, X, Y, Z. This is the position vector of a general point on the line. Now, depending on what the value of lambda is, you get different points on the line. Okay, just like here, X, Y used to represent a general point. Here, R represents a general point, and it's written in this form, X, Y, Z. Okay, and instead of inputting values of X, like we used to do here, to find corresponding values for Y, here we have instead a parameter that we call lambda. We input different values of lambda to get different points on the line, and lambda is going to give us the values of X, Y, and Z. So this is X, no, sorry. For instance, in this case, when we input lambda equal to 1, this is X, this is Y, this is Z. Okay. So that's the idea of the equation of a straight line in vector form. Now, you need two things to write down the equation. The equation is going to be written in this form. Okay, you need two things to write down the equation. One is position vector of a known point. So you need to have a point on the line, position vector of that. And the second thing is the direction vector. You just input those two values and you get the equation of the line. This is how the equation of the line looks like. You're not going to actually input a value of lambda here because lambda could be anything. I'm just inputting these values to show you how you could get different points on the line. But the equation, if you're asked about the equation of a line, you're just going to leave it in this form like this. Okay. Now, let me write down an example here. Let's say you want to find the equation of a line given certain information. Find the equation of a line L that passes through the point P with position vector OP, which is, let's say, 1 minus 4, 3. Given that the line is parallel to another vector, let's say it's parallel to this vector 2, 5, 1. It's parallel to this vector. Okay, we want to write down the equation of this line. How do you write down the equation? You write down the standard form that you have, R equals A plus lambda D. All you have to do is input values here. A is a point on the line, a position vector of a point in the line. We know that. 1 minus 4, 3. Let's input that in place of A. Plus lambda into D. D is the direction vector. Remember what D is? D is direction vector, which means any vector that is parallel to the line. We know that this vector here is parallel to the line. So the direction vector is 2, 5, 1. You input that here, and that gives you 2, 5, 1 like this. And that is the equation of the line that you have. Okay. This is what we were looking for. This is the vector equation of a line. All right, now let's quickly quickly try to relate this to the coordinate geometry form. You see, you have a point here. You used to have a point here as well, C, right? That was the point. Then you had m times x. X was the value that you were inputting there. In this case, you input lambda to get the point. Lambda multiplied by the direction vector. In 2D, the direction used to be represented by gradient. Now, gradient is not defined for 3 dimensions. Gradient was defined only for 2 dimensions. That was y2 minus y1 over x2 minus x1, change in y over change in x. In 3 dimensions, we instead use direction vector. So in 2-dimensional form, m used to tell us the direction, gradient used to tell us the direction of the line. In this form, this vector d tells us the direction of the line. So that's what you need to write down the equation. You need 2 things: position vector of a point on the line and the direction of the line. Okay. Now, how does this give us every point on the line? It basically works like this. Let's say you have a line like this, okay? And there's a point that is the origin here, okay? What this line should give us is the equation of this line, the equation of the line represents the position vector of every point on the line. Right? This line's equation should give us the position vector of every point on the line. Now, let's say this is what a line looks like. And this is where the origin is. What is position vector? It's the vector that joins the origin with that point. Okay. Now, how does this equation give us every point on the line? In this case, point P is what we were given. We were given the position vector of the point P, which we input in place of A here. That is one point that we're inputting in this equation. So let's say that is somewhere here. Okay. So this first vector, what is this going to give you? We're going to give you? It's going to take you from origin to this point, OP. Okay. That is what this first part of the equation gives. Then you have lambda into 251. Now, what does 251 represent? 251 is a vector that is parallel to this line. Okay, vector that is parallel to this line. So due to this vector, once you have reached this point, you're going to move parallel to the line like this in this direction. Okay, so once you've reached this point, now the second vector is going to make you move parallel to the line like this. Okay, so in the direction of the line. So that is why every point that you get from this equation is going to lie on this line, because we have already reached the point P that was any particular point on the line. And then the second vector is parallel to the line. So that is in the same direction as the line. So after P, you can only move on this line. Now, the value of lambda is going to decide whether you move to the right side or the left side. For example, if lambda was positive, you might be moving in one direction, so maybe in this direction. If the lambda was negative, you would get a point in the other direction. Depending on the magnitude of lambda, if it was 1, for instance, that would give you 1 point here. If it was 2, it would give you another point. If it was 0.5, it would give you another point here, and so on. So different values of lambda are going to give us different points on this line. Why on this line? Because after we have reached the point P, we are moving along the line after that because of the second vector. Okay, if the lambda's value is big, you would be far away from this point on this line. If the lambda's value was small, you would be somewhere close to this point, but again, you would still be on the line. All right, so that's how this equation kind of works to give you every point on this line. Okay, that's the idea of the equation of a straight line using vectors. Okay, if lambda was 0 here, you would get point P because this would become 0 and you would get point P. Positive values of lambda might give you points on one side and then negative on the other side. Okay, so what do you need to remember from here now? This is the standard form of the equation of a line. You need to remember the standard form. R equals A plus lambda D. A stands for the position vector of a particular point on the line, and D stands for the direction vector. Now, let's quickly take an example on this. So now you should be looking at the second vectors worksheet. We will be doing some questions from that worksheet now. Let's start with something very simple. First of all, vectors worksheet 2. Okay. Now, for now, I'm only going to look at the first part of this. It's mostly just a 1-mark question, finding the equation, and then in the next part, you have to use that equation to do something else. Let's try this. This is question number 5 from the worksheet. We are only going to look at the first part for now. We have these 2 points, A and B. They have their position vectors given relative to the origin, O. OA and OB, we have their position vectors. There's a line L that passes through A. So A is a point that lies on the line, and it's parallel to OB. Given this, we need to state a vector equation for the line L. Okay, that's pretty straightforward. What's the standard form of the equation of a line? R equals A plus lambda into D. You just have to input these values. A is a point on the line. Since it's parallel to OB, that means this is going to give us the direction of the line. So in place of A here, you can input -135. Plus lambda into D. In place of D, you input this, which is 3 minus 1 minus 4. And that gives you the direction of the line, the equation of the line that you're looking for. Okay, that's the equation of the line. Let's take another example. Again, just focus on the first part for now. This is another question, only first part of this. Question number 15 from the worksheet. Okay, so it says, with respect to the origin O, the points A and B have position vectors OA equal to this and OB equal to this. The point P lies on the line AB and OP is perpendicular to AB. In the first part, it says, find a vector equation of the line AB. Line AB, we need an equation for this line. Remember the standard form for the equation of a line, that's R equals A plus lambda D. Okay. Now there are 2 points, A and B, for which we have their position vectors. We know OA and we know OB. We know their position vectors. So it's essentially something like this, that you have a line. On this line, you have 2 points. Or in fact, let's actually do it this way. You have 2 points. There's one point A and the other point B. There's some origin somewhere. There's an origin somewhere. Okay. You are given two vectors, OA and OB. These are the two vectors that we're given. You're asked to find equation of the line AB. What's the line AB now? It's a line that passes through the points A and B. It might look something like this. It's a line that passes through both of these points, A and B. So what do we input in this equation now? R equals A plus lambda D. Now you could input any one of these 2 points here, right? A and B, they both lie on the line. So you could use any one of those 2 points in place of A here. If you use OA, for instance, what is that going to be? I 2j 2k. If you write this in vector form, it's 1 2 2. What about the other one? 3i plus 4j. If you write this in vector form, it would be 3 4 and 0. There's no k component, so that's 3 4 0. You could use any one of these 2 points. Either use 1 2 2 or 3 4 0. Use that here, so that is going to give you 1 2 2 plus lambda into d. In place of d here now, you need to write down the direction vector of this line. How do you find the direction of this line? We're not given that here in the question, but we know that points A and B lie on the line. So what we can do from that is we can find the vector AB. We can find the vector AB. Now, A and B both lie on the line. So the vector AB is going to be in the same direction as the line. So we can say AB is the direction vector of the line AB. Okay. So you can find the vector AB and say that that is the direction of the line. Let's try that. Can we find the vector AB from this? The vector AB is equal to OB minus OA, position vector of the second point minus the position vector of the first point. What do we get from this? 3i plus 4j minus I plus 2j plus 2k. This gives us 2i plus 2j plus 2k. This is the vector AB. You can leave it like this, or if you write this in vector form, it would look like this, 2, 2, 2. This is the direction of the line. Okay. I'm sorry, this is minus 2k, not plus 2k. So this is 2, 2, and minus 2. This is the direction of the line AB. Okay. You've got both of these things now. You have a point 1, 2, 2. Direction of line is 2, 2, minus 2. So the equation is going to be 2, 2, minus 2 here with lambda. And that is your equation of the straight line. R equals 1, 2, 1, 2, 2 plus lambda into 2, 2, minus 2. All right. Now in coordinate geometry, we used to have a unique equation every time. Every line had a unique equation. For example, one possible equation could be 3x plus 4y equals 5. No matter what point or gradient or what point you choose on the line, the equation would turn out to be this in simplified form eventually. Okay. You could have 6x plus 8y equals 10, for instance. That's also fine. It's the same line. But in simplified form, you would always get a unique equation, right? But in vectors, we often have multiple equations representing the same line. There are multiple ways of writing the same equation. So for instance, in this case, what we did was we used the point OA as this point A. What if we used OB instead? You could do that as well. You could use OB as well. In that case, the equation, the line's equation would become OB, which is 3, 4, 0, plus lambda into the direction, which is 2, 2, minus 2 in this case. This is another possible equation of this line where we are using the other point. Instead of 1, 2, 2, we are using 3, 4, 0, and this equation is also correct. Okay. Now that's one thing, that you could use any of the 2 points here in place of A. The other thing is the direction vector could also be something else. Essentially, any multiple of this vector would work here. Okay. So for instance, other possible direction vectors in this case could be instead of 2, 2, minus 2, we could say 1, 1, minus 1, right? That's the same pattern between the components. 2, 2, minus 2, if you would take 2 common from this, you could write it like this, 2 into 1, 1, minus 1. So this vector is in the same direction as this vector. We could use this instead as well, instead of the direction vector. You could use 1, 1, minus 1 as well. Similarly, you could also use 4, 4, minus 4, or 3, 3, minus 3. So essentially, any vector that is parallel to this vector, you could use that as the direction vector here. So all of these vectors could be used as direction vectors. Make sense? All right, so you have multiple possibilities. Your direction vectors could have multiple possibilities as well. And this line, this point that you have, you could use any of the given points. Okay. In this case, you had 2 points given. You could use either of them. The direction vector is turning out to be this. You could use any multiple of this, any scalar multiple of this. You could multiply this by 2, 4, 5, or simplify this to 1, 1, minus 1. All of these are correct possible direction vectors for this line. All right. I hope that makes sense. Now let's move on and discuss the concept of parallel and perpendicular lines. So we learned how to write down equations of lines, right? Now, what about parallel or perpendicular lines? Let's say we have 2 equations and we want to determine whether those 2 lines are parallel or not. Okay. Let's say there's line L1 and there is another line L2. L1 has this equation, R equals -2, 5, 3 plus lambda into 2 minus 1, 3. And there's another line that has this equation, let's say 5, 2, 1 plus, in place of lambda, since we have already used lambda for one equation, for the other equation, we can use another variable, let's say mu. You'll see this being used a lot in the equations as well. So if you have already used lambda, the other line cannot have the same parameter. You'd have to use a different letter for that. You could also use A, B here if you want. In fact, A is going to confuse you. Maybe M, N, or P, Q. You'll see other letters being used here as well. You'll sometimes see U being used or T being used. All of that, all of those are okay. You can use any letter. It doesn't matter. Okay. So for the other equation, we're using mu here. And let's say this equation is mu into -4, 2, and -6. Okay. What we want to do is, we want to determine whether L1 and L2 are parallel lines. This is what we want to determine. Okay. Now remember what we used to do earlier. We have learned how to prove that two vectors are parallel. For proving prove vector is parallel, all we did was we just divided the corresponding components. If the result turned out to be the same for all of them, we said that the vectors are parallel. Okay. But now we're not talking about vectors. We're talking about lines. We have equations of lines. How do we prove that these lines are parallel? Now remember, for a line, the direction of the line comes from this vector. This is the direction vector of the line 1 and line 2. Okay, these are the direction vectors of the lines 1 and line 2. All we have to do is just check whether these direction vectors are parallel or not. Okay, that's all that we need to check here. So don't worry about the rest of the equation. We want to prove or determine whether these two lines are parallel. For that, only thing that matters is the direction of the line. Okay. So what is the direction of the line one? Of line one, that's 2, -1, 3. That's the first line. Direction of the second line is -4, 2, and -6. We need to determine whether these lines are parallel. We can just divide their corresponding components. 2 over -4, that gives us -1 over 2. -1 over 2, that is also -1 over 2. And 3 over -6, this also gives us -1 over 2. Now, since their direction vectors are parallel, since the direction vectors of L1 and L2 are parallel, the lines L1 and L2 are parallel. All right, so if you are looking for, if you're looking to find whether the lines are parallel or perpendicular, all we have to do is just check whether their direction vectors are parallel or perpendicular. And that is enough to figure this out. Okay. So let's take another example. Let me just write down this whole scenario again. Let me just copy this whole thing. I'll erase some of it. We could use the same idea for perpendicular vectors as well. So let's assume we want to determine whether L1 and L2 are perpendicular lines, and I'm going to change the direction vectors here a little. Let's say we have these two lines, and now one direction vector is 2, -1, 3, and the other is, let's say, 6, 3, -3. We want to determine whether lines L1 and L2 are perpendicular now. Remember what we used to do for perpendicular lines? We used to check perpendicular vectors. Two vectors are perpendicular if their dot product is equal to 0. Now, in this case, we're not talking about vectors, we're talking about lines, equations of lines. We have these two equations. How do we prove that these two lines are perpendicular? Again, all we need to worry about is the direction of the line. That's all that we care about, because direction is going to tell us whether they are perpendicular or not. So we just take their direction vectors. 2, -1, 3. This is the first direction vector. Dot the other direction vector, which is 6, 3, -3. And we just evaluate this thing. So it's 2 into 6 plus -1 into 3 plus 3 into -3. Let's see what this turns out to be. 12 -3 -9, and that is 0. Now, since the dot product is 0, we can say since the dot product of the directions of both lines is equal to 0, L1 and L2 are perpendicular. All right, so in order to prove that two lines are parallel or perpendicular, all that you need to do is just check whether their direction vectors are parallel or perpendicular. Okay. Now let me actually just copy the statement from somewhere. Let me find this, if I can do that here anywhere. Vector equation and parallel and perpendicular. Yeah. So this is what you need to remember from this now. In order to check if two lines are parallel or perpendicular, you need to just check if their direction vectors are parallel or perpendicular. Okay. Similarly, if you were asked to find angle between two lines using their direction vector, using their equations, all you have to do is find the angle between their direction vectors, and that is going to give you the result. Okay. So whenever you're talking about any angles, we just use direction vectors. Okay. I hope that makes sense. Now let's move on and discuss the concept of points of intersection of two lines. Let me see if we can do that today or that tomorrow. Monday, Wednesday, and Tuesday. We have this one here. Okay, now let's actually continue with this tomorrow, inshallah. In the next class, we will learn how to find points of intersection of two lines given their equations. And also, hopefully, we can also cover how to find perpendicular distance between a point and line. So we would want to complete our concepts tomorrow. And then we will spend one more day on some more practice questions. Hopefully we can complete the concepts tomorrow. If not, then you might have to spend an extra day on this, but let's see. Okay, that's it for today. Let me just remind you what we've done today. This is the vector equation of a straight line, r equals a plus lambda d. R equals a plus lambda d. This is the vector equation of a straight line. A here is the position vector of a known point on the line. D represents the direction vector of the line. Okay. I'm sorry about that. Just erase this. It becomes a bit cleaner. Okay. So this is the vector equation of a straight line, r equals a plus lambda d. You need to remember this form. So in order to write down the equation, you need to input two things. Position vector of a point on the line, which is a, and direction vector of the line, which is basically just any vector parallel to the line. Okay. So that's how we write down the equation of a line. Then we learned how we did a couple of examples in this, and then we learned how to determine whether two lines are parallel or perpendicular. All you have to do is just check whether their directions are parallel or perpendicular. Okay, just using that, we can determine whether those lines are parallel or perpendicular. In the next class, we will be talking about intersecting lines, finding points of intersection of two lines. Okay, that's for tomorrow. I'll see you again in the next class then. Allah Hafiz.